So for section 11.2, properties of power series. So in this section, we will introduce power series and we will find the radius and interval of convergence. Number one, before we begin with the actual topic, let's have a look at what we have done so far. So far we have worked with series, with constant terms, and we have determined whether they converge or diverge. All right, so on the previous chapter, we went over many of the tests. There's actually 10 different tests to determine the convergence or divergence of a series. But now, what we're going to do is we're going to look at series. We're going to work with series with variable terms that represents functions with series. All right, how do they look like? Well, very similar to the series that we did before, but now this time you will see this letter x. So that's the variable, and well, depending on where the series is centered at, it may look like just an x, which is centered at 0, or if it's centered somewhere else, that's centered at another value. In a very similar way to Taylor and Maclaurin series. Maclaurin series are centered at 0, while Taylor series are centered at the origin. So yes, here's what the note is going to tell us. So the power series in x minus a is centered at a. Okay, in x minus a, it's called a power series centered at a, and when we see just the letter x, it's just a series centered at the origin. And like we mentioned before, we can think of this as a function f of x equals sigma n equals 0 to infinity a sub n, some rule, times the center value to some power n. All right, and just like any other function, we are going in a way to find the domain, evaluate, to find the convergence or divergence, as you will see soon. Okay, so but before working with what we actually will work about finding the interval of convergence, let's play with some power series here. So we are given here a couple of examples, expand a few terms for the given series. Well, so all we have to do, in a very similar way that we did it with series of constant terms in the previous chapter, not with variables this time. So the counter goes for the n. X remains there. So what we're going to do here is x to the 0 plus x to the first plus x to the second plus x to the third plus etc. We don't have to write too many of them. That's going to give us, well, x to the 0 is 1 plus x squared plus x cubed plus etc. All right. For example, for letter B, well, we have more n's to plug it in. So we're going to have -1 to the 0, x minus 5 to the 0 over 0 factorial plus -1 to the first, x minus 5 to the first, 1 to the first, plus -1 to the second, x minus 5 to the second, over 2 factorial, plus -1 cubed, one more, why not, plus dot dot dot. Remember, those 3 dots denote that the series is going forever to infinitely many terms. All right, okay, let's simplify this. 0 factorial we know is 1, -1 to the 0 power is 1, and x minus 5 to the 0 power is also 1, so that's going to give us a 1. And then, well, be careful with the next sign, because we're going to have -1 to the first power, which is -1, x minus 5 to the first, that's going to be x minus 5 to the first power over 1, plus, in this case plus, because -1 squared is positive, 1 x minus 5 squared over 2 factorial. Let's just leave it. Yeah, let's expand the 2 factorial is 2. The next one would be negative because negative 1 cubed is negative 1. X minus 5 cubed over 6. And of course, I mean, we could write more terms, but let's just stop there. Okay? That's fine. It's just expanding a few terms. Very similar to last chapter. Now, of course, in the last chapter we did something like this, but reverse. We were given a series in expanded form. They were going to ask us more often than not to write it in sigma notation, and in fact, it's important to be fluent in this kind of exercise, in this type of problems, because some homework problems will ask you to find the radius and the interval of convergence of a series, but you won't be given the series in terms of sigma notation. They will give you the polynomial form, so you need to figure out the series in sigma notation form. So, well, of course, how do we start? Well, number one, a good thing to start with, well, of course, sigma, yep, n equals to infinity. Okay, it could be n equals 1, it could be n equals 0. Well, we'll figure it out. I know the general form. If we go back to the general form, I have it here starting at 0, but incidentally could be starting at another value other than 0. Could be starting at 1 or 2 or at 2, 4, etc. It doesn't matter. So, well, in this case, so we have x's. So yes, there's going to be an x to, let's see, okay. X, how about to the n? And start the series at n equals 1. Yes, and to the first, and then we have an invisible 1 here. Yes, that sounds good. And then we have the sequence of numbers 1, 8, 27, 64. Does that look familiar? Doesn't that look like the sequence of cubes? That is 1 cubed, 2 cubed, 3 cubed, and 4 cubed. Those are the numbers in the denominator. So that's an n cubed. And that's the series in sigma notation. Let's look at the next example. Sigma n equals, no, I don't think I'm going to start this at 0 because notice the power of x minus 5 right here. It's an invisible 1, and then 2, 3, etc. So it goes from 1 to infinity. And this is going to be, okay, number 1. Notice also that the series alternates negative, positive, negative. So we need a negative 1 to the n. And of course, for n equals 1, the first term, negative 1 to the first power, yes, that's going to work. It's going to give us the negative number here. Looks great. Now, what else do you observe here? Something very interesting, a very interesting pattern here. Do you see this one here? It's also there. Do you see this 2 here? It's also here. Do you see this 3? It's also there. All right? So it seems like an n times x plus 5 to the n should work. But what about the numbers in the denominator? Okay, so we have 4, 5, 6. So we have 1, 4, 2, 5, 3, 6. We can think of the difference between 1 and 4. So what's the difference between 1 and 4? What's the difference between 2 and 3? How about in the denominator having an n plus 3? All right? Because if n equals 1 plus 3, that's going to give us a 4. N equals to 2, 2 plus 3 equals 5, etc. So this should work. All right? So that's just a little bit on working with power series. Now let's define what the interval of convergence is. Okay, and the interval of convergence, it's nothing other than like finding the domain of a function, because like we mentioned before, these power series are functions of series. So we're finding the interval of which the series will converge. So when it comes to finding the interval of convergence. So for example, if x is assigned a value, then its power series becomes an infinite series with constant terms, you know. And but of course the thing here is that depending on the choice of x, that's the important thing here, that's the real deal. Depending on its value, we have many different tools to determine whether the series converges or diverges, those tools that we learned before. All right, now that set of values of x for which the power series converges in an interval centered at a, possibly at 0, possibly at another value of a other than 0, depending on the series. That's what we call the interval of convergence. So here is the thing. We may view the power series sigma a sub n x minus a to the n as some function of some function f whose domain coincides with the interval of convergence. Okay, so let's add a few more bits to this idea. Okay, so suppose you're given f of x equals 3 over x plus 4. All right, evaluate f of 2. Okay, so 2 over, or rather 3 over 2 plus 4 equals 3 over 6, which equals 1/2. All right, and then what about f of 2? No, not f of 2, I mean f of -4. That's 3 over -4 plus 4, and that's a 3 over 0. What's this? Isn't this undefined? So in a way, what we want to find here is the domain of the function. So the domain is x such that x is not equal to -4, because otherwise the denominator becomes a 0 and then it's undefined, or in interval notation, -infinity to -4 union 4 to infinity. All right. So in a similar way, we're going to work with power series. So let's consider this series sigma n equals 0 to infinity, and let's put this like x over 3 to the n. Let's work with something simple, and of course this is some function f of x. All right, trust me, you will see later how this is going to be a rational function. But well, I don't want to spoil the whole plot of the movie just yet, but you'll see the connection later in this chapter. All right, so let's see, what about f of 1? Okay, so for f of 1 we get sigma n equals 0 to infinity of 1/3 to the n. And well, what about the series? Does the series converge for the power series converge for x equals to 1? Well, what do we have here? Convergent. We have a convergent geometric. All right, so it works. Now, what if on the other hand, for example, what about f of 5? So in the place of x, I'm going to plug in the value of x equals 5. So 5 over 3 to the n. So in this case, well, this is also a geometric series, but look at the value of r is 5/3, and the value is unfortunately larger than 1, greater than or equal 1. So this is a divergent geometric. All right, this is divergent, that's convergent. Well, so do we have to plug in every single value to find that in a way that domain, or which in this case is the interval of convergence? Because that's what we're interested in, the interval of convergence. I mean, because why would we be interested in the interval of divergence? I mean, something that diverges just blows up to infinity and that's the end of the story. But in this case, for applications, we need to find, we're interested rather in the interval of convergence of a series, of a power series more in particular. So, well, so of course we cannot do this f of 1, f of 3, we cannot check every single value of x in the same way like back in algebra, back in intermediate algebra, we were not able to just plug in any single value, infinitely many values, right? Of course, there were different rules to find the domain, like in this case, what I did is to set the denominator equal to 0. For radical functions, you set of even index, you set the radicand greater than or equal to 0, solve the inequality, and for logarithmic functions, you set the argument of the logarithmic function greater than 0 and solve the inequality. So what's the process then to find the interval of convergence? Okay, that's on the next page. So interval of convergence. So for a power series, so there's three possibilities to find or to classify the interval of convergence. The number one possibility is the series will converge only at its center, x equals a. Second possibility, the series converges for all x. That is, you can plug in any value to a given series and it will converge for any value of x. And the third, and the one that we're going to be working for a while, it's this one. There is a positive number r such that the series, if absolute value of x minus a less than r, and converges if that, and diverges otherwise with well. What does that mean? Okay, number one, let's do a mini review of intermediate algebra. For example, x minus 3 less than 4. Can we do something smaller? Less than 2. Okay, so when you solve the inequalities like this in intermediate algebra, what you did is, well, get rid of the absolute value bars, x minus 3, and then set this greater than negative 2. Well, and then add 3 to the 3 sides of the inequality to get 3 minus 2, that's 1, less than x, less than 5. All right? So most likely they just told you to do this, but ultimately, what's the concept here? What is this inequality really representing? Well, this inequality is telling me the values of x that are 2 units away from the center 3. And if we plot this on a number line, so this is my 0, 1, 2, 3, 4, 5, 6. Okay, so all the values that are between 1 and 5 are 2 units away from 3. Okay, so or less rather. So for example, if my center is 3, all right, I'm going to count 2 units to the right and 2 units to the left. All right, 2 units, 2 units. Aren't these endpoints really the solution to the inequality, the endpoints of this compound inequality? So that's what that represents. And for example, for a given series that it's centered at whatever value, it may only converge at its center. It may converge for all real numbers, or it may converge for only a limited range, which in this case that's or rather a limited what's it called, interval. And it could be parentheses for both, brackets, both brackets, one parenthesis, one bracket, or etc. We will see a few examples about this one. So let's go ahead and look at an example, of course. So the best way to see this in action is by seeing this in action. Okay, but now what's the process that we follow? So here's the thing. What we're going to do is we are going to perform the ratio test to this power series. So let's set it up. Let's set up the ratio test. So we need to find the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And well, where a sub n plus 1 is all this expression right here, replace n with n plus 1 and everywhere. So that's going to be limit absolute value, well, n approaches infinity of absolute value of n plus 1 x plus 2 to the n plus 1 divided by 3 to the n plus 1 plus 1. Isn't that going to be 3 to the n plus 2, really? And divided by a sub n, where a sub n is just the original. So n x plus 2 to the n over 3 n plus 1. Alright, so you could do this, you could write it like this, which is fine. However, you know what? And I would recommend you do this so you don't spend too many steps doing this. So what I'm going to do instead is, instead of dividing by the original problem, I'm just going to multiply by the reciprocal. 3n plus 1 over n times x plus 2 to the n. Alright. And well, from here, let's start simplifying anything that we can. So number one, it seems like we can rewrite this 3 to the n plus 2. Okay, so let's go ahead and do that. Limit n approaches infinity of the absolute value bar. Well, yes, we need the absolute value. I'm not going to erase them yet. So that's n plus 1 times, okay, this x plus 2 to the n plus 1, we can write it as x plus 2 to the n times x plus 2 to the first power. In the denominator, we can write 3 to the n times 3 squared. Okay, I'm going to leave it as 3 squared for now. Of course, that becomes a 9, but you'll see what's going to happen anyway. And can we make this look like a 2? And 3 to the n plus 1, that's 3 to the n times 3 to the first, divided by n times x plus 2 to the n. And from here, we may cancel a lot of stuff. You'll see. So we can cancel x plus 2 to the n with x plus 2 to the n. We can cancel 3 to the n with 3 to the n. And we can cancel 3 to the first with 1 power here, to be left with a 3 in the denominator. Alright, so after doing all these calculations right here, we will be left with the following. So, limit n approaches infinity, n plus 1 times x plus 2 over 3n. Okay, now be careful here when it comes to the next few steps. Well, here notice that our limit, the dummy variable for the limit is n, so we will be looking at n plus 1 over 3n. This x plus 2 should be taken outside, because I know x is usually a variable. Yes, that is true. But in this case, the variable for which we're computing the limit for is n. So we're going to take this x plus 2 as a constant outside of the limit. So, but in this case, because x can be any value, so we're looking at, if we want to find that interval of convergence, we need to keep these absolute value bars. And these 3 right here, we can write it outside. And then we're going to be left with limit n approaches infinity of the absolute value of n plus 1 over n. And well, what do we have here? N to the first power, n to the first power, polynomial over polynomial. This limit equals to 1. Oh, this is supposed to be a 3. And that's a 1/3 x plus 2 times 1, which is this limit. All right? But I mean, what's this? Okay, well, one more step. Why not? So we're done with 1/3 times absolute value of x plus 2. But how do we go from here to find the interval of convergence? Well, because we are using the ratio test, recall that for the ratio test, okay, let me write it down. For ratio, converges when the limit is less than 1, diverges when limit is greater than 1, and it's inconclusive when the limit equals to 1. So we want to find the interval of convergence. Then we need to set this 1/3 absolute value of x plus 2. We need to set it less than 1 in order to find those values of x that will make this series converge. In a similar way that for the rational functions, we set the denominator equal to 0. For logarithmic functions, we set the argument greater than 0 to find the domain. For power series, when we use, in this case, the ratio test, we set the final limit less than 1, because that's the condition for convergence. If we were otherwise investigating the interval of divergence, well, then we would have set this inequality greater than 0. But no, we don't want to find the interval of divergence. Why? I mean, again, if it diverges for whatever values, and that's the end of the story, we're interested in the interval of convergence. So let me set this inequality on the side. So that's a 1/3 x plus 2 less than 1. Okay, let's multiply both sides by 3. That's x plus 2 less than 3. And well, let's break this inequality into 3 pieces. X plus 2 less than 3, but also greater than -3. Subtract 2 to both sides. Not to both sides, actually to the 3 sides. And we're going to have -5 x less than 1. All right, so far our interval of convergence is potentially the following: -5 to 1. That means any number that you plug in, any number between -5 and 1, exclusive for the endpoints, excluding the endpoints, that you plug in here for x, will give you a series that will converge. All right, otherwise, if you plug in exactly -5 and exactly 1, you will get a divergent. You may get, so that's what we need to test. So we need to test that part. So here is the thing. Okay, let me take that back. Here is the thing. We could have this both parentheses. It could be possible that converges at the endpoints as well, or it could be the case that converges on the lower endpoint, diverges on the upper endpoint, or diverges on the lower endpoint and converges at the upper endpoint. So that's to be determined, and that's what we're going to do in this case. How do we do that? Well, so in this case, we will test the endpoints. Okay, so test x equals, well, usually we start with the smallest one. So sigma n equals, sigma n equals 0 to infinity of n times -5 plus 2 to the n over 3 to the n plus 1. Okay, let me write down that -5. And notice when we plug in that value of -5, we no longer get a power series. It's now a series of constant terms. the x has gone. And that's negative 5 plus 2, that's negative 3 to the n, 3 to the n plus 1. All right, and now, well, this series looks complicated at first glance, so it would be a good idea to actually simplify this. N equals 0 to infinity, n times, okay, this negative 3 to the n is the same as saying negative 1 to the n times 3 to the n. And in the denominator, 3 to the n plus 1, that's 3 to the n times 3 to the first power. And the good thing here, check this out. This is going to simplify. Goodbye. Whoops. And well, we're going to end up with a new series. So, and in fact, you will see this negative 1 to the n times n over 3. N goes from 0 to infinity. All right. So this is the new series that we need to check whether it converges or diverges. And here is where we're going to use all the techniques, all the tools that we learned in the previous chapter. All right, so I mean, look at this negative 1 to the n. So for sure, we can use the alternating series test. Okay, so let's label this as alternating series test. All right, and for the alternating series test, well, the first condition is that the limit of a sub n approaches 0 is a 0, and the second condition is that the sequence is non-increasing, that is a sub n plus 1 is less than a sub n. All right, so let's check the first condition for this one. So limit of n over 3 and approaches infinity. Well, this is infinity, which is not 0, so diverges. And we're done with this endpoint. All right, so because it diverges for the lower endpoint of x equals to negative 5, we can go back to our interval of convergence and put a parenthesis. So the next to be determined at the upper endpoint of x equals to 1 is maybe it's parentheses or maybe it's a bracket. We'll see. Let's have a look. Okay, so test x equals to 1. And what do we have? So we have sigma n equals 0 to infinity, and that's n times 1 plus 2 to the n, 3 to the n plus 1. Okay, let's replace x with 1, and n equals 0 to infinity. So that's n, 1 plus 2, that's a 3 to the n over, okay, we can simplify this 3 to the n times 3 to the first. And check this out. This one is going to cancel again. And also, well, the final series is going to look similar to the previous one, except that in this case, it's not alternating. It's simply n over 3. And well, for this one, we can simply, well, we will have to look at a different test. So in this case, it's not the alternating series test. So in this case, it will be, okay, let's see. How about just the n-term test for divergence? Yep. N-term test. All right, we can perform the n-term test. And for the n-term test, recall that test only tells us about the divergence of the series. It doesn't tell us anything about the convergence, and if the limit is 0, recall that the series is that the test is inconclusive, and then we have to check with another test. So in this case, well, let's find the limit, And number 3, n approaches infinity. Well, infinity, which is not equal to 0, which is great. This means that diverges. The series diverges. Alright. Going back to the interval of convergence. So that's going to go from -5 to 1. Alright. On both cases, exclusive for both endpoints. Okay. So